Uh, Thank you for coming to my session, and it's great to have all of you here at the Spark AI Summit 2019. So this session is about probably two of the most critical properties our customers as well as the community expect from us. And these properties are correctness and performance. So firstly, please let me introduce myself. So my name is Cheng Lian. I'm a software engineer in Databricks. I've been here for 5 years. And I'm also a PMC member and committer of Apache Spark and a committer of Apache Parquet. So Databricks is founded by the original team who created Apache Spark, and we provide a unified platform that accelerates innovation by unifying data science, engineering, and business. Right now, our products is available in both Microsoft Azure and Amazon AWS. Here is a small example set of what does Databricks look like across the industry. And at the core of our ecosystem, here is the Apache Spark. But to get Spark into production, we need to interface with two different worlds. So first we have the developers and all kinds of CI tooling, produce and test the build. And to run the Spark in cluster, we also need other fancy technologies in the place, like containers and the schedulers and cloud providers, et cetera, and et cetera. And at the end of this pipeline, there are our customers. And it could be a data scientist, data engineering, and also since Spark is a general processing framework, the applications could come from a very different, diverse industries. So at Databricks, for Databricks Runtime, which is built upon Apache Spark, we have a release process dependent on Apache Spark. So for example, Databricks Runtime 5.0 contains Apache Spark 2.4, and each new version, we will have a testing period and then get released, and then we provide full support for it. And we also support long-term versions. So our goal here is to make releases more frequent and automatic while keeping on a high quality bar. And this, and in terms of quality, within the scope of this session, we're mostly talking about the correctness and performance. So here we'll present the main software stack we use to tackle this major challenge we have inside Databricks. As you may already know, Apache Spark is a very active open source project, and many contributors from all over the world contribute tens of pull requests every single day. And at this place, mistakes are bound to happen. Although the community and the committers, we are trying very hard to review the pull requests and to catch all of those bugs prematurely. However, we cannot prevent all of them. And so we need some tools to make sure that we can catch as many of these potential issues and as early as possible. So where do these contributors go into Spark SQL and like Spark SQL Core and the Catalyst Query Optimizer? So in terms of a line of code, it's about 50-50. And we can see that in terms of a line of code, it seems that the testing coverage is pretty good. However, unit testing is not adequate. It does not cover enough. It doesn't provide enough tester coverage. For example, Spark SQL provides over 200 built-in functions. And for all these functions, we can have a different size of data. We can have a different data with different properties, like bigger ones, smaller ones, sparse ones, or dense ones. And also, some of those functions behave differently with different configurations and feature flags. So we really need to try to search a really big search space and to test as many things as possible to catch as many bugs as possible. So in the typical testing pyramid, firstly, we rely on unit testing and then integration tests and finally end-to-end testing. However, this is not enough to automate and ensure high-quality builds. So we need to add something more. For example, we will need to ensure plant stability, which means that the very same SQL query is always parsed and constructed into a stable query plan that is reproducible, so that when we have an issue, we can reproduce this issue in a precise way. And we also need to run micro benchmarks in order to catch some minor regression issue lurking in some performance critical code path. And in addition, we also need fuzz testing, so that basically we feed random data and random queries into the system, so that we can hopefully catch more issues. And also stress testing, so that we can ensure that the system is stable enough and doesn't have performance regression. And in terms of the performance regression, we also leverage a larger scale TBCDS and other standard benchmarks to do macro benchmarks. For example, inside Databricks, we run TBCDS benchmarks at 1 TB scale on a daily basis and a 10 TB TBCDS on a weekly basis. Yeah, and also we try to run some of the typical customer workloads. Some of those customers are generous enough to just provide exactly the same workloads for us, so that we can cover their use cases. And in some other cases, we try to simulate the real world workloads. So as an overview, the whole CI pipeline we built inside Databricks starts when some new code got merged and a build is triggered. So with some new artifacts produced by this pipeline, we started the correctness and performance test, which produces different metrics. And these metrics need to be analyzed, and we apply different policies, and then we try to catch any exceptions and validation errors or other events. So let's zoom in into the last box in the next slides. So when trying to scope and address the impact of every single event arriving into the system, we try to divide these events into different categories. For example, correctness errors or performance-related errors, like performance regression. And then we drill down into this error, try to replicating the issue and try to minimize the testing data and compare with previous releases. And if we identify that those issues or those events are actually legitimate issues, we will send alerts to relevant team members. Okay, so let's start with the correctness issues first. So what does correctness really mean here? What do we really care? So in the context of Apache Spark SQL, it basically means that whether a query can finish gracefully. And by gracefully, it means that for those queries that are invalid, the system should produce a meaningful error message instead of just a crash or splitting tons of meaningless exceptions or stack traces. And more importantly, for valid queries, the system should produce correct answers, which is non-trivial to determine in some circumstances. So let's have a look at the overall structure of our pipeline. So what we want to do here is to generate some random queries and some random input data, and then compare the answers produced by Apache Spark SQL with the answers produced by other standard SQL systems. And inside Databricks, so we chose the PostgreSQL. However, this itself still doesn't provide enough coverage. So in addition to that, we also compare the answers from different Spark versions, or the answers provided by the same Spark version but with different configurations. And in order to achieve this, we're defining a query profile containing different SQL features and then translate it into either the PostgreSQL dialect or the Spark SQL dialect. So the random query generator works in two steps. So firstly, we need to generate some random data sets. So we begin with a randomly generated schema, a random number of tables and rows, and then fill the tables with totally random data. And in general, we favor smaller data sets so that we can speed up the tests. And now we have the data sets at hand, and we can move on to the actual query generation. So typically, a SQL query consists of multiple clauses. Like if you want to filter something, you get a where clause. If you want to do some fancy aggregation, you get a group by, and so on and so forth. And some of those clauses may contain 0 or more expressions. And even some expressions itself may contain nested queries in the form of subqueries. And so this is really a recursive query model. And so with this recursive model, the random query generator basically follows this model and try to generate the queries and execute them against those random data sets we generated in the previous step. So if you think about it, this is basically the reverse step, the reverse process of a SQL query parsing. And so with these tools at hand, we can easily generate and compose different target SQL features and test them. So while generating a concrete SQL query, we may assign different weights to various SQL features to control how often a specific SQL feature appear in the randomly generated queries. So there are two kinds of weights, independent weights and interdependent weights. So independent weights are assigned to things like independent optional query clauses like union, group by, where, or different optional types of expressions appearing in the select clause. And interdependent ones can be used to test features like join types and select functions. And for example, if we already decided to have a join and a generated query, and we may further decide what kind of concrete join types we want to test inside the generated query. And also, if we decided to have a window function and a select clause, we may also use this kind of techniques and to decide what kind of a window frame we want to use. And next, let me present two concrete real-world correctness issues we caught in the past using this framework. So here is a messy, randomly generated SQL query that ran perfectly on PostgreSQL and produced a correct answer, but somehow failed on the Spark SQL. And the failure was actually an analysis exception, so which suggests that the Spark SQL's analyzer considers this query as invalid and simply rejected it. So you may see that we caught this issue used relatively use the RQG framework with relatively small data sets and a relatively fast speed. So for now, let's just ignore the detailed expression in this query and focus on the overall shape of this query. You may see that this query contains a join, contains aggregation, and the join operator joins two tables, one of which contains a complex filter predicate. And by analyzing the actual exception message and the stack traces, which are omitted here for saving spaces, our hunch was that the issue probably lurks in either the projection or the filter. And to make further analysis easier, we try to minimize this query plan by sampling one subtree at a time. And in the end, we can minimize this query into something like this. So this is basically the minimal plan we obtained that can still reproduce this issue. So what happened here? So you see that in the selector clause, there is a nested coalesce function call. And inside the Catalyst optimizer, there is actually one optimizer rule that was too smart and tried to flatten this nested coalesce call in the selector clause. And usually this kind of optimization is preferable since it indeed saves some SQL function call overhead. So the optimized query looks like this shape. You can see that the problem of this one is that the grouping key expression no longer appear in the selector clause. So you can see here that the coalesce foo.id, foo.val is the grouping key, and after the optimization, it is gone. And this run optimization caused an analysis error. So the second example query did pass the analyzer, but produced a wrong answer. So as you can see that Spark SQL produced a double value, while PostgreSQL actually produced a none. So this is a quite severe problem since the lead is a very commonly used built-in window function. So the shape of this query is much simpler than the previous one. It doesn't contain any joins, and the where clause only contains really just a dummy predicate, and that is always evaluated to true. So the query plan looks like this. It's simply a project over a filter over a scan. And using the similar techniques we employed in the previous example, we can basically shrink the original SQL query into something to the right side. And after some further analysis of this issue, it turned out that using constant input values breaks the behavior of the lead function. Unfortunately, we caught this issue relatively fast with the RQG framework and fixed it quickly and pushed it back to the upstream. So since we are creating schemas and queries in a random way, we also want to assess how fast we can reach a certain level of coverage, how fast we can converge. So imagine that there is a new PR and we want to do some testing, and for how long do we have to test? How do we have to test so that at least all of the available operators are exercised at least once? So the chart here on the left plots the x-axis, the number of queries run from 0 to 500, and on the y-axis, the number of distinct operators got exercised. Operators and expressions got exercised. So we split nodes, different SQL nodes into expressions, which is in blue, such as and, or, equal, plus, blah, blah. And also physical plant operators, which is plotted in red, such as filter, project, window, sort, etc. So the columns on the right here show the top 10 popular expressions and operators that are generated from the RQG framework. So we can infer from the chart that the number of operators quickly grow close to the maximum, and within about 500 queries, we basically reach a stable coverage in both metrics. So running 500 queries takes about maybe 15 minutes on using a single Spark worker. So this is relatively fast and provides us a relatively good coverage. So this information basically helps us to determine when should we cut down the RQG, because the framework itself can just keep generating queries and running those queries day to day. Of course, this does not mean that all Spark operators are exercised, because the RQG framework, right now, this RQG framework can only exercise features that can directly access via SQL language. And we are also working on improving this framework so that we can compare some. We can also test some features that are not directly available in the SQL language, but are available in terms of, for example, the data frame DSL. And for this kind of a comparison, we're planning to do some future work in the Spark vs Spark comparisons. And also, RQG itself, as I mentioned previously, it only uses the relatively small data sets so that we can speed up the tests. And it does not cover big data. And for big data, we really want to use our performance test toolings and to test that part. So this leads us to the second half of the presentation, which is performance testing. So same as correctness testing, whenever the framework helps us find a performance regression, we root cause it and alert relevant team members if this is a legitimate issue. And for performance testing, we use two major tools, two major benchmarking tools, which are the Spark SQL Perf library and the Async Profiler. So the Spark SQL Perf library is an open source performance testing library dedicated for Spark SQL. And typically, we run various TBC benchmarks regularly to track performance variations. And the second tool, Async Profiler, allows us to produce flame graphs, looks like this, so that we can drill down and do some fine-grained performance analysis to find out performance hotspots. So here is a historical dashboard we used to track down the performance variations when we were releasing Databricks Runtime 5.0, which corresponds to Apache Spark 2.4. 2.4. So let's focus on the chart on the top first. So the x-axis at the daytime we ran around the TPC-DS benchmark, while the y-axis showed the execution time. So basically, lower is better. And you can see that the green line, which is a Master 2.4, that is a development branch we are focusing on, there is about a 15% performance regression. So 15% might not seem a big regression, but this is actually the big issue. And we treat this one seriously inside Databricks. And you can see that at the bottom left, we can also show the top 5 regressing queries comparing to previous versions, and so that we can drill down actual slow queries and to try to figure out the actual reason behind the performance regression. And in this case, we picked in this 67th query inside TPC-DS, and we found that there is actually a 18% regression. And the runtime was from when running in Spark 2.3, it takes about 5 minutes, and in Spark 2.4, it takes about 6 minutes. So in order to analyze the root cause of this performance regression, we leverage the async profiler and produce some flame graphs here. I guess most of you already are familiar with a flame graph. So basically, in this graph, the redder the line is, it means that the slower this function call takes. So here we generated 2 flame graphs, one for Spark 2.3, one for Spark 2.4. And I'm not sure whether you can spot any differences between these two. It's kind of hard, but let's zoom in. You will be able to see that there are, on the left, there are mostly 2 humps, while on the right side, there are 3 humps here. So there are probably something wrong. Unfortunately, the flame graph toolset provides some sort of methodology to compare compare the diff to flame graphs, and then we have something like this. So the redder ones mean that the function call is slower, and the white ones mean that this function call didn't appear in the previous one, but appeared in the newer ones. And here we can see that we found some new functions like murmur3 hash UDF, 8 string and something, and also something related to unsafe and some memory management and stuff. Especially the new function called that murmur3 x86 blah, blah, blah. This function is a nice signal because we can use this one to git bisect and to figure out which commit added this one, and that commit is probably at least partially contributed to this issue. And using this technique, we can easily root cause the issue, and we did find one commit that did some major refactoring and originally it tries to improve some performance and stability issues. However, accidentally it introduced some regression. And after doing some benchmarking ourselves, we, by comparing the new and the old implementation, we did find that in Spark 2.3, the hash unsafe bytes function takes like 40 microsecond, while the Spark 2.4, it takes 140 microsecond. So this might not be a super big difference, but if you are, for example, hashing all of the SQL, all of the strings in your table, it might cause a severe performance regression. And also the UTF-8 string.getBytes function got slower in the newer function, in the newer version. And in order to fix this issue, we basically firstly opened a pull request and tried to fix this issue. However, I found that it's actually relatively hard to address this issue, and we decided to revert a few commits. So this is really a journey to get a release out, because it takes time to root cause all kinds of performance issues, but it really pays off. And after about a month, we reduced we basically eliminated this 15% performance regression, and actually made Apache Spark 2.4 faster than Apache Spark 2.3. And actually, this journey pays off very quickly. So if you look at the performance dashboard we track inside Databricks, the performance of Spark 2.4.1 is almost twice of the performance of Spark 2.1.1. And so here, this is basically the number we generated using TBCDS. So for different workloads, this number may vary in different ways. So in conclusion, Spark in production is not only a framework, because when you are running a Spark in production, there are a lot of environmental issues. For example, the JDK versions you are running, the operating system versions you're running, maybe you are running a Spark inside a Docker container, and maybe your Kubernetes is imposing too much resource limit to your container, and et cetera, et cetera. So unit tests and simple integration tests cannot really provide a great tester coverage. And also, although this random query generator tool is already very helpful for us to spot all kinds of different issues ahead of time, there are still a lot of Spark-specific issues that cannot, Spark-specific feature that cannot directly access via the SQL language. Those features cannot be exercised very well through this framework. And as I mentioned previously, we are also improving this tool internally so that we can catch these issues ahead of time. So we really need some Spark-specific tools to automate this whole process so that we can ensure both correctness and performance. Okay, so this basically concludes my talk, and thank you. So we still have about 10 minutes here. If you have any questions, don't hesitate. Thank you.
Yeah, we have about 10 minutes. For anyone who came in while the talk was going on, if you have any questions, please line up at this microphone or the microphone on the far side, and we'll alternate questions.
Hi, great talk. I just want to kind of know, is there any kind of sense of completeness in terms of tests on the coverage of the SQL language, meaning like the entire Spark SQL? How do you judge the completeness? Because like the test is like the data set is randomly generated in.
Right. So firstly, by randomly generating all kinds of queries and expressions, it already kind of improves in the tester coverage. It already is strictly better than just writing specific unit tests and integration tests. And also, as one of a few slides in my talk mentioned, we actually tries to track how many distinct operators we actually exercise. And so this kind of provides some signals about coverage and completeness, but this one cannot guarantee 100% coverage, because even if you covers all these operators, you cannot cover all the combinations. So we just do basically try our best. And if we find out that in some case, we do miss some important cases, then we can do several things. Firstly, for example, if we missed some operator in the framework, we add it into it. And also, if some patterns are more, how to say, it's easier to introduce bugs into some components or some operators. We may increase the weights when generating the actual queries, so that that part get exercised more frequently.
I see. Another question is like, I know all the operators, some of the operators actually work on different data type. For example, like sum, or it works on in or long or whatnot. So do you actually also test this in terms of the performance over different types?
Yes. As discussed previously, when generating the data sets and the queries, we firstly pick a random schema. So and the actual queries are generated according to that schema. Because the schema is random, the data types have a column there as random, and then different input types are exercised for different expressions.
I see. This is very cool. Thank you.
Thank you.
Yeah, so I have a question about adaptive execution. So I saw the feature was listed on the keynote. So what is the status of the adaptive execution? Do we already have the adaptive execution? What is the performance?
You mean how does an adaptive execution affect the performance and how do we track this?
Yeah. Also, there's a configuration about the reduce partition number, right? So if we have the adaptive execution, is that the configuration still works?
Sorry, what was your?
I mean, that configuration will be deprecated if the.
Okay, got it. Yeah, that's a good question. So for Spark 3.0, the adaptive query execution feature is based on contribution from Intel, and one of the biggest improvements that we're doing for Spark 3.0 is try to generalize the whole adaptive execution framework so that it's easier and more intuitive to build more advanced features like automatic skew triage and also tuning partition numbers automatically. And so performance-wise, whether these are useful, we can have several possibilities. For example, Spark SQL already have a cost-based optimizer. So after regenerating the query plan according to intermediate statistics, we can compare the new plan and the original plan to see which cost is lower, and then always choose the better one. And also the performance testing framework we introduced here can also help us to catch at least for TIP-CDS and some of our customer workloads, we can ensure that this feature doesn't regress. For example, maybe the cost model we chose is not good enough, and there is some inaccuracy here. I'm not super sure about the configuration improvements, but I just say because adaptive execution is still based on all kinds of estimation. So I just say there probably will be some cases that there will be performance regression, and you may want to turn off this feature. And in that case, those old configuration options are probably still useful, at least before this whole feature set stabilizes.
Okay, I see. Thanks.
So first of all, so I have to say I am sorry I made such a performance mistake. That's my commit code cause of my performance regression. So my question is in the future to avoid such a performance regression or performance fault. So do you have any plan to publish or make it public this performance framework? Performance framework or performance result as a public for also for open source Apache Spark version.
Okay. So firstly, thank you, Kazaki-san, for the question and for your long time contribution. Every single one makes this kind of mistakes. I probably make a dozen of them, so there's no need to apologize. And yeah, we built all these tools using all kinds of open source tool sets. And however, internally, we're still testing this thing, and it is actually kind of hard to tune all these configuration. For example, the question the previous attendee asked about completeness. We do want to have some more intelligent ways to do that. And so internally, we still need to do some manual tuning in order to produce some helpful information and signals. And on the other hand, what we really want to achieve is that we internally run this tool for the whole community and for all of our customers, so that you don't really have a need to run the thing. But I think in the future, when we think that this whole thing is polished enough, there is a possibility that we will push this to the whole community. And this will be helpful, for example, if you are extending Spark SQL, like you are extending the DDL, the DML, adding more features, and you want to test your own configuration or your own customization, and it would be helpful.
Yeah, I hope so. It will be available soon.
Thank you. Okay, if there are no questions, I think this is it. Thank you, everyone.